This is a work with colleagues at IMT Atlantique, where I am, and Université de Brest, so not that far from here. And it's about basically dealing properly with ODEs that are on symmetric positive definite matrices using Lie group integrator theory. And first, I'll try to motivate why we may want to be interested in ODEs on covariance matrices. Well, I switch between SPD and covariance matrices by basically starting from a motivation in machine learning. By learning dynamical systems, that's one thing that we like to do in our group, to solve inverse problems, mostly in earth sciences, but not only. So I'll spend some time motivating the problem and then explain the basic idea behind Lie group integrators that apply to Lie groups, obviously, but also homogeneous spaces, which is a structure that we can give in multiple ways to covariance matrices. And I'll show a few examples that stem from stochastic differential equations when you look at their moments of order 2. So to have compact and flexible representations of those. So as I said, we like to deal with dynamical systems in physical sciences in our group, mostly about dynamics of the ocean or also remote sensing. Here you have sea surface height data and models, and also remote sensing, optical remote sensing data, multispectral, with long time series of that, and we're interested in modeling with or without prior knowledge on the dynamics, have compact representations of them to help them solve inverse problems in the end, like interpolation, denoising, forecasting, and so on. So often those dynamical systems are modeled through differential equations, either fully known or specified, but they can be complex, chaotic, and so on, or in some other cases, they're only partially known or maybe fully unknown, but can be observed through huge data sets. So in that case, we want to learn a representation of the dynamics from data, either from scratch, just using the data, or having only partial knowledge of the ODE. We do that for many reasons, but one key scientific issue is to deal with uncertainty. In earth sciences, basically making a forecast in 10 days, think about weather forecast, is basically meaningless if you don't have an uncertainty associated to the prediction. So that's one aspect that we want to tackle. So we need a framework that can help us do uncertainty modeling, quantification, and propagation. So lots of applications. And so we need stochastic representations of dynamical systems. So there are basically two types of uncertainties that we'd like to be able to handle. The first one is the one due to the initial condition that may be uncertain and has to be propagated forward in time. So basically that's the push forward of the initial distribution from the flow. And the other one is that the dynamics themselves may be uncertain. Okay, so in that case, you may have the dynamical system in itself introduces uncertainty. So a nice mathematical framework that can help us handle both phenomena is SDs, stochastic differential equations. So dx of t, if x is your state, the state of your system, you have a drift term and a diffusion term with bt, Brownian motion. So that's the basic representation that we are interested in. And now the question is, since we want to integrate such system, but if we don't know them, we also want to learn them using machine learning, we need to parameterize them. So we have several different ways of doing that. One that we've tried, maybe the most natural, but maybe not the most convenient, is to do some kind of maximum likelihood estimation of operators L and F that you parameterize, for example, through neural networks. And you want to maximize the joint density that you can factor since you have a Markovian system. So you have ways of doing maximum likelihood estimation. So we've done that in the paper. Another way is to switch from SDs to PDs and deal with the Fokker-Planck equation. It's no easy task, especially numerically. So theoretically, it gives you all the info on the PDF, the probability density function of the solution. But it's very hard to work with, except in small dimensions or in simple cases, which are not always interesting in practice. Yet another way is to use generative models. more machine learning oriented, like if you're familiar with that literature, of course, GANs, but also normalizing flows and diffusion models more recently, and variants of that. So I'm not going to talk about that today, but we also do that. In that talk, I'll talk about rather moments-based representations where, okay, SDEs are maybe complex, but if I use the moments of order 1 and 2, I come back to ODEs and I can use them to represent my process. Of course, it will be a partial representation, except in the Gaussian case, but in applications, it might be good enough in many cases. So basically, we parameterize stochastic dynamics with a process on the mean and the autocovariance, so gamma ST. And in this talk, I will even restrict myself to gamma TT, so the variance, the actual covariance of the system. But we could extend those results to the full covariance if you wanted to. So if I give you an SDE in the wild, you have its expression, you can get ODs on its moments quite easily. For instance, if you take this classical one, which is the Ornstein-Uhlenbeck process, multivariate here, so linear drift term and constant diffusion sigma. In that case, it's very simple. The solution is Gaussian for Gaussian initial conditions. And you can derive easily equations on the mean and covariance. You just write out the integral of the solution, take the expectation for the mean. So as you would expect, you get only a linear equation. For the covariance, it's slightly harder. You just have to apply a bit of stochastic calculus, Ito's lemma first, on X transpose and work through the computations and you get this in the end. So you have a term like that. The derivative of P is AP plus PA transpose plus a term that stems from the diffusion. So working with these ODEs instead of the SDEs can be an alternative because you basically we have lots of techniques to learn ODEs, so this is convenient. We can switch to our well-known techniques. The problem, of course, is that SPD matrices do not form a vector space. It's a smooth manifold in R to the n times n, with n the dimension of the state. And that's why we need to be careful when we numerically integrate them. So if you take the example of the sphere, it's very visible. As soon as the right-hand side of such an equation is always a vector in the tangent space. So as soon as you apply a classical Euclidean method in the embedding space, well, you typically leave the manifold in the case of the sphere. So if you want to do something meaningful, you either have an intrinsic method that respects the geometry of the sphere, or you try to project back somehow on the sphere and see if it works. For the SPD matrix cone, it's maybe not that bad. The tangent space, so it's the set of symmetric matrices. You can identify it to that space at any point. But it's maybe not that bad as with the sphere because it's an open set. So it means that as long as you're taking a small step, you will stay in the manifold, unless you're already on the boundary. But still, there are some cases where 2 large steps will leave the manifold. So we've formalized this through a theoretical result. I'm not going to go into details. If you're interested, just check the paper. But basically, we're able to quantify this. For small enough time steps, we can provably stay on the manifold for, maybe any numerical integration scheme like Euler or Runge-Kutta methods. They will be based, in the Euclidean case, as rho t plus 1 equals rho t plus some step times a vector field. For the Euler method, it's directly the right-hand side of the equation. For Runge-Kutta methods, might be a bit more involved. But basically what we've said is that if the right-hand side is SPD as well, it's always symmetric but not systematically SPD, then you don't have any issues. It's very easy to show. But if it is not, we have bounds on the steps so that we can either guarantee that we stay on the manifold or we can guarantee that we actually leave the manifold. And these bounds are based on the eigenvalues, ratios of eigenvalues between the right-hand side and the current iterate. So I'm not detailing this further, but we have ways of checking whether it's actually necessary to use geometric methods or Euclidean methods would be good enough at least to stay on the manifold, not from a precision numerical accuracy point of view. So in the case when you do need it, we use Lie group integrators that apply to Lie groups, but more importantly, homogeneous spaces. So we need 2 ingredients, a smooth manifold, here the SPD manifold, and a transitive Lie group action on the manifold. Here, so we only consider matrix Lie groups so that we can express the group operations easily. And once you have those two ingredients, you can define an infinitesimal version of the action that takes an element of the Lie algebra and an element of the manifold and outputs something in the tangent bundle. It's defined like that. So as often in Lie groups, you come back at the you take the derivative and take the group action on a curve that starts at the identity with initial speed, some element in the Lie algebra, and differentiate and take the value in 0. And that's how you define the infinitesimal version of the action. And once you've done that, you've chosen all these ingredients, you've computed the infinitesimal action, and you can, the theory says is that you can tackle all equations in which the right-hand side can be written using that infinitesimal action. And the nice thing is that you have a bit of freedom. You have the form of the equation is constrained, of course, but you still have freedom on this function psi. You can make it depend on time and on the current iterate if you want. I'll show how it works right after. So the simplest method you could think of would be the Euler method applied to the Lie groups. So the good news is that if you have an equation like on the bottom here, you can show that if you take the Lie group of the homogeneous space, you have a very simple equation that's linear but with variable coefficients. And if you are able to solve that equation, you can just come back to the manifold using the group action. So it already suggests, even if psi might not be constant, a numerical method, just freeze x and t temporarily, integrate the linear equation in the Lie group just using the Lie group exponential, provided you're able to compute it efficiently, and then come back to the manifold using the group action, update the parameters, and so on. So you already have a Euler method. So that's very simple. For Runge-Kutta methods that we've applied here, it's a bit more involved because you need to be able to play with vector fields, add them to points on the manifolds. That's not something that you can do in the Lie group. So you have to use a vector space. In that case, that vector space will be the Lie algebra. Without detailing too much, there is an equation in the Lie algebra that you can use. It's defined here. It uses the derivative of the inverse of the exponential map. So it's a bit complex, but this can be approximated using compositions of the commutator, the matrix commutator for matrix Lie groups. But once you have solved that, it's just a regular linear equation, so you can use any classical method that you want. You can combine vector fields, and you can define Runge-Kutta methods. So here we've done it for Runge-Kutta 4. Details are in the paper. Okay, so now if you want to apply this to covariance matrices, we have to define all the ingredients. So the most important one is the Lie group and the group action. Here we've used the most simple. Just take the action of invertible matrices by left multiplication and right multiplication by the transpose. Very, very common. We could do many things that would be more complex and more elegant, but numerically, we're still in the process of doing that, and numerically it might not be better, not necessarily richer in terms of the equations that you can handle. So for simplicity, I'll stick to that one in that talk. So you have that group action. If you go through the math and define the algebra action, you actually come back to the right-hand sides that you can handle that are MP plus PM, with M which can be a function of P and of time if you want to. So if you come back to the example I showed first, it corresponds to the first two terms very naturally of the differential equation, and with some tricks on playing how you define the psi variable, you can actually also incorporate the constant term. But you'll have to invert a matrix. That's the price. Anyway, once you it may seem restrictive, but depending on the way you define psi, you can actually integrate a lot of differential equations. So I'll show you another example in the next slide, but also there are also examples that stem from optimal control and Riccati equations. If you're familiar with that, many of those types of equations can be put in this framework as well. But it's not exactly the same application, and I'm not going to talk about it here. So let's take an example that stems from an SD. So at first glance, you could say, okay, it's the same as before, but no, the diffusion this time is dependent on the state, so it's much harder to handle. And here well, you have to choose the dimensions of the Brown motion well for things to work, but it's not that very important. The thing is that the diffusion is dependent on the state. So you have a paper that works through all that theoretically. You can derive the equations in that case on the mean and covariance, same using stochastic calculus. And here you have a second term that's dependent on P and M. So the equations are actually coupled here, except that the first one is easy to solve, so not really. But it goes in our framework. If we define psi as this function, we're able to use geometric integration in that case and make sure that we won't leave the manifold and maybe hope for better performance at each iteration. So that's what we've done here. We've taken two numerical simulations of the SDE, and this is the flow of the covariance matrix. So here it's in 2D so that we can visualize things numerically. So using the embedding, taking the upper triangular part of the matrix and putting that in R to the 3. So as long as you're in the cone, you're good. And if you leave the cone, well, it means that your numerical method had an issue and you cannot interpret the results in terms of a covariance matrix, which is critical in applications. So what we did is that we qualitatively compared the trajectories and compared to the Euclidean method, a reference with a very, very small time steps so that we're sure that everything goes smoothly. And also a kind of Riemannian version where we use a Euclidean method and project back using the exponential map in that case for the Fisher-Rao metric. So very naive, but at least we can stay on the manifold using that technique. So, and what we see is that in the left case, everything stays on the manifold, but our method is by far the most precise with a relatively large time steps, but in practical applications, you don't control that. And in the right-hand side, with a different parameterization, the Euclidean method actually immediately leaves the manifold, and then it's done. You can stop your integrator; it's useless. And both the geometry-aware versions stay in the manifold, but ours is much more closer to the actual the reference trajectory with a very small time steps. So it's encouraging. We've actually quantified that using Riemannian distances on the SPD cone. Well, I think I'll skip it because the conclusions are the same, just with it quantified. And I'll conclude. The motivation stemmed from managing uncertainty in dynamical systems, very important for us, for our applications. And one way of representing this uncertainty is to use first and second order representations of stochastic processes, but you need to be careful with covariance matrices. So we've been able to design Euler-Runge-Kutta integrators. So that was Runge-Kutta 4, but any Runge-Kutta method, we can define it explicit, as long as it's explicit. Because we are able to take advantage of the structure of homogeneous space. And as I said, it also applies to many other equations, including in optimal control, but we are working on that. And the next challenge is, okay, we wanted to do learning at first, so that's the next step. And it's reassuring to have these kinds of numerical methods in machine learning, because if you're calibrating an equation from data, at first it will not be the right equation. So it will be very wild, it will vary very quickly, and you have to make sure that you stay in the manifold. Otherwise you cannot train anything, you cannot iterate on that. We're working on applications to real data sets where the equations are unknown. And also on the geometry side to use better suited Lie group actions. So I've talked about one possibility that was suggested in the reviews was to use the symplectic group, and it's very neat. If you do that theoretically, you get exactly the Riccati equation that arises in optimal control, but numerically it's not obvious that it's better. So we're working on that. And also, if you want to have an actual generative model, be able to integrate trajectories, we need also to account for the full covariance. So gamma T of S and not just gamma TT. But we have ideas on how to do that. And of course, this applies to any homogeneous space. So, for example, it could apply also to dynamics on hyperbolic spaces and many others. And a few references if you're interested. Thank you.
Thank you very much. Now we have maybe 1 minute for the question according. Is there any?
Thank you. Very nice talk. Just a simple question: do you worry about rank in some of these integrators?
No, but I guess we could. Here, I'm not sure. Maybe can you be a bit more specific about?
Depending on the rank, that would be questions of invertibility, or whether you're close to the to the boundary. To the boundary.
Yeah, of course. We haven't worried about it yet, but as long as it's not the initial condition, in which case you will probably run into issues. I'm not sure it's a problem as long as it's asymptotic. In the example I showed, actually the solution always converges to 0. So it's not a problem in that case, but I guess you could account for, if you want to account neatly for when you're on the boundary, you have to change the space you're into. But I'm not sure how easy it is to do, but I guess it's doable if you find the right parameterization of your rank up to k covariance matrix. I guess it wouldn't be that difficult, but we haven't done it. But it's a good suggestion.
Okay, maybe just a very, very short question or comment. If not, then let's thank the speaker again.